In the last videos, we've been considering hidden Markov models with discrete hidden states. What we're now going to move on to is considering hidden Markov models with continuous valued latent or hidden states. And in particular, a type of model called the linear Gaussian state space model, or LGSSM. Okay, so let's walk us through what the new setup is. So again, we've got latent variables X and observed variables Y. And in this case, we're going to assume that our latent variables are vector quantities. So they're going to be k-dimensional vectors, and they're going to have real valued elements. That's what this thing means up here. And we're going to take an exactly analogous approach like we did before, where we put a bigram model on our discrete hidden latent states before. Now we're going to put a Gaussian AR1 process on those instead, because they're continuous valued quantities and they're vectors. So here is the expression for that. We assume that the rule from transitioning from xt to state xt from xt minus 1 is given by a Gaussian distribution with a mean which is just a matrix A times the previous hidden state here, and a matrix Q here describing the correlated noise, which is possibly added to that mean value to corrupt it a little bit. So just to sort of make sure we're happy, the matrix A here is going to be a K by K matrix, and this is going to be a K by K covariance matrix here. Okay, so we also need to fully specify this Gaussian AR1 process. We'd also need a distribution over the first state. I've not explicitly put that on the slide because it's not of central importance here, but just to be complete, that's also going to be a Gaussian distribution with a mean, let's say is called mu1, and a covariance, let's say sigma 1 in here. Okay, so this, and these are both vectors, of course, this sort of fully specifies the distribution over the latent component of the model. Let's look at the observed variables now. The observed variables we're going to assume are d-dimensional, and again real valued, so they can be positive or negative. So this is different from the dimensionality of the hidden state. Hidden states k-dimensional, observed states d-dimensional. And again, we're going to use a Gaussian distribution for these variables. So the emission distribution down here is another Gaussian, and the mean of this Gaussian is just going to be a linear function of the observed variables. So you take matrix C, you multiply that by the vector of latent variables. This matrix C is d by k dimensional, and you add some correlated Gaussian noise to that mean in order to generate Y, and the covariance of that noise is R. This is a d by d matrix, a d by d covariance matrix. So notice here how all the distributions are of Gaussian form, and all the relationships between those variables are a linear transformation of another latent variable or another variable plus some noise. So you can see by this that everything here is linear and Gaussian, hence the name linear Gaussian. And then state space model sort of applies to this hidden state of the x's here. So everything here is linear and Gaussian, and that means the whole joint distribution over all of the variables, so the y's and the x's, you can think of this as a big joint Gaussian. If I stacked all of the variables y1 to t into a big vector and the variables x1 to t into a big vector, you could view them all as being generated from a Gaussian with a massive mean vector and a massive covariance matrix as well. So everything is jointly Gaussian. The reason why we're doing that and looking at this model is because then learning and inference become really easy, because you're essentially computing properties of Gaussians, admittedly in this slightly strange context. So all of the equations that you need to do, say, inference and estimation of hidden states, that all turns out to have nice closed form solutions. Okay, what I want to do now is just run you through some of the properties of data that you can get out of this type of model by looking at a simple example. And I'm just going to make a little bit of space for us to explore that example here. And it's a kind of an unusual example. I'm going to look at an example where we've got k equals to 2 latent variables. So it's sorry, the dimensionality of our latent variables, to be more precise. So that means our state xt, you can break it up into the two components, x1t and x2t. Okay, that's why that's coming from k is equal to 2. And their observed variables, they're just one dimensional. Okay, so big D is equal to 1. And I've plotted some examples of latent variables and the y's here down at the bottom. So just to make this a bit bigger, this is y and this is x. And again, this is time down here. So the blue line shows one of our latent variables. I think that's probably x2. Let me just write that in here. So this is x2 of t, the second component of the latent variable vector, and this is x1 of t. And then, of course, the bottom shows y of t. And what you can see from this is they look a bit sinusoidal. There's sort of a regular repeating pattern in them. They're noisy, though. The amplitude of the sinusoid and maybe its phase are wandering around a little bit. And what I want to do is walk through these settings for the parameters that I've chosen here and show how that behavior is connected to those parameters. And sort of chief amongst them in terms of this suspicious behavior is this matrix A. So here's the matrix A. Remember, this is the dynamics matrix in here. That looks like this constant lambda in here, which is given below, and is very, very close to 1, times a matrix which involves sines and cosines. So that's the first bit of the model. The dynamics here, Q, that's the covariance of the noise on the noisy dynamics. That's given by this matrix down the bottom here, 1 minus lambda squared times an identity matrix. So this is showing that we don't have any correlated noise, that noise is added to x1 and x2 independently in this transition model. So I can actually write that up in a slightly different form, which is going to be informative in a minute at the top of the slide here. So we can say x of t is equal to a matrix A times x of t minus 1. And then we know we're adding independent Gaussian noise to the x1 and x2 component. That's what this is showing. This is what it's saying here. So I can say this thing, we're going to add, I can write this as the following way. We're going to add 1 minus lambda squared, that's the variance of this noise here, times a vector of noise variables where this noise comes from a standard Gaussian with 0 mean and identity covariance. This is just a 2D vector drawn from two independent mean 0, variance 1 Gaussians. So this is an alternative way of writing these things. And let's just actually substitute in for the value of A in this case. This is 0.99 times cos of theta minus sine of theta, sine of theta, cos of theta. And then this thing is a vector, x1t minus 1, x2t minus 1, plus 1 minus lambda squared. Let's just make everything in component form, x1t, epsilon 2t. Okay, so this is an alternative way of writing out the Markov model component of our model. Okay, so one thing that hopefully is sort of piqued your interest is this thing in here, of course, is a rotation matrix. This is the matrix you need to multiply something by in order to rotate a vector by an amount theta. So there's a really useful diagram we can do here if I just zoom in to sort of better visualize what's going on. Let's plot x1 along the bottom axis and x2 along the top axis here. And we can visualize what this rotation matrix is doing. If we have, if we describe our hidden state by a vector at time step, let's say t. So this is, let's take it at xt minus 1. So this is the vector described by a hidden state at t minus 1, plotting out the two components of the vector as components of this phasor. What the dynamics do is they apply this rotation matrix here, this rotation matrix. So this rotation matrix is going to rotate that phasor by an amount theta. And theta here is 2 pi over 10. So it's going to be 36 degrees. So it's going to rotate this by 36 degrees. And then in order to get our, I'm just going to make us a bit more space here, in order to get our next setting of the latent state, we're then going to add some Gaussian noise to this vector. So this is defined the mean of the state. I should say, importantly, one thing I missed off is you then shrink that vector by a tiny amount. So we've rotated it by 36 degrees and then multiplied it by 0.99, which will make it 1% smaller. So this thing rotate and shrink, the two steps here. And now we're going to add in this noise component over here. And the noise is independent, as we said. And if you remember, lambda is taking a value of 0.99 here. So 1 minus lambda squared, that's going to be a really small number because it's almost 1 minus 1. So the amount of noise we're adding is going to be kind of small here. So we're going to sprinkle a small amount of Gaussian noise in here. Maybe the contour of one variance looks, of a single variance away from the mean looks like this. And we sample the next setting of the latent state, and that gives us xt. And now we repeat that process to sample subsequent vectors of xt. We rotate it again. Maybe that goes up here. And we add Gaussian noise and sample it. And then we rotate and shrink again. I keep forgetting the shrink part. And sample Gaussian noise, and that gives us this one. And we rotate, shrink a little bit, add Gaussian noise, and so on and so forth. So we keep doing this process, and you can see that over time, the phasor defined by the latent state is going to rotate around, not in a perfectly sinusoidal way because of the Gaussian noise that we're adding. And again, this factor of shrinkage out the front here is playing exactly the same role as lambda in our first order Gaussian autoregressive model. It's damping out some of the noise. So if the factor of at the front was set to 1, this phasor's magnitude would eventually explode to infinity because we'd be integrating up more and more noise. The fact that we're shrinking away is damping out the noise and making sure this has a well-defined limiting distribution. In fact, you can show that the marginal variance of this process is 1. So the marginal variance of x1 and x2 is going to be 1. I'll leave that as an exercise to the reader. Okay, so take-home point here is that the dynamics here specify a noisy sinusoid, and the components of x capture the x and y component of that noisy sinusoid. You can view it as a complex sinusoid if you like, and the x1 component is modeling the real valued part, and x2 the imaginary valued part, if you want to take that attitude. Okay, so that's the unobserved state. Let's quickly take a peek at the observed state here. So and how that relates to the unobserved state. So in a bit more detail, you'll see C takes this value here. This is the matrix C. It's 1, 0. So you can see this is going to pick out the first element of X. So I can write YT is equal to the matrix C, which is 1, 0, times X plus a small amount of Gaussian noise. Maybe use a different symbol for this. Okay, so YT by this multiplication just picks out the x1 component of our phasor, the real valued component, if you like to think of it that way, and adds a tiny bit of Gaussian noise on with very, very small variance at each point. So it looks like I labeled my x1 and x2 here correctly. You can see that the y value here looks like the black curve up here at every time point. So if I draw this across at simultaneous time points, you can see that y is an ever so slightly noise corrupted version of x1 of t in line with these expressions up here. Good. Okay, so what's the point of this? Well, the point of this is to show that these linear Gaussian state space models can encode noisy sinusoidal behavior. So they can model characteristic frequencies in data. You could have multiple of these sinusoids by summing together these types of dynamics in your latent state. And then, as I said before, they also capture sort of decaying exponential behavior and exploding exponential behavior. And through this, you can essentially implement any type of linear system you like in your latent and observed state. It's linear systems which are driven by noise and possibly corrupted by noise as well. And this is why these types of models are really useful in things like control and signal processing, because you can capture linear dynamics using these types of models. Okay, so I hope this has given you a good flavor for what kind of behavior linear Gaussian state space models can capture and why they're useful.